Hello everyone, today I tell you about information of science. What is science? First of all, please subscribe my channel and press the bell icon for more and interesting videos. So let's start. History of science. For the academic journal, see History of Science journal. New Science redirects here. For the treatise about history, see the New Science. Newton's reflector, the first reflecting telescope, part of a series on science. Essence, show, branches, show, society, show, outline, portal, category. The history of science is the study of the development of science and scientific knowledge, including both the natural and social sciences. The history of the arts and humanities is termed history of scholarship. Science is a body of empirical, theoretical, and practical knowledge about the natural world, produced by scientists who emphasize the observation, explanation, and prediction of real-world phenomena. Historiography of science, in contrast, studies the methods employed by historians of science. The English word scientist is relatively recent, first coined by William Whewell in the 19th century. Before that, investigators of nature called themselves natural philosophers. While observations of the natural world have been described since classical antiquity, for example, by Thales and Aristotle, and the scientific method has been employed since the Middle Ages, for example, by Ibn al-Haytham and Roger Bacon, modern science began to develop in the early modern period, and in particular in the scientific revolution of 16th and 17th century Europe. Traditionally, historians of science have defined science sufficiently broadly to include those earlier inquiries. From the 18th through the late 20th century, the history of science, especially of the physical and biological sciences, was often presented as a progressive accumulation of knowledge, in which true theories replaced false beliefs. More recent historical interpretations, such as those of Thomas Kuhn, tend to portray the history of science in terms of competing paradigms or conceptual systems within a wider matrix of intellectual, cultural, economic and political trends. These interpretations, however, have met with opposition, for they also portray the history of science as an incoherent system of incommensurable paradigms, not leading to any actual scientific progress but only to the illusion that it has occurred. Early Cultures main article, History of Science in Early Cultures. See also, Protoscience and Alchemy. In prehistoric times, knowledge and technique were passed from generation to generation in an oral tradition. For instance, the domestication of maize for agriculture has been dated to about 9,000 years ago in southern Mexico, before the development of writing systems. Similarly, archaeological evidence indicates the development of astronomical knowledge in preliterate societies. The development of writing enabled humans to store and communicate knowledge across generations with much greater accuracy. Many ancient civilizations systematically collected astronomical observations. Rather than speculating on the material nature of the planets and stars, the ancients charted the relative positions of celestial bodies, often inferring their influence on human individuals and humankind. This demonstrates how ancient investigators generally employed a holistic intuition, assuming the interconnections of all things, whereas modern science rejects such conceptual leaps. Citation needed. Basic facts about human physiology were known in some places, and alchemy was practiced in several civilizations. Considerable observation of macroscopic flora and fauna was also performed. Ancient Near East. The ancient Mesopotamians had no distinction between rational science and magic. When a person became ill, doctors prescribed magical formulas to be recited as well as medicinal treatments. The earliest medical prescriptions appear in Sumerian during the 3rd dynasty of Ur, c. 2112 BC, c. 2004 BC. The most extensive Babylonian medical text, however, is the Diagnostic Handbook written by the Umanyu, or chief scholar, Asagil-kin-apla of Borsippa, during the reign of the Babylonian king Adad-apla-iddina 1069–1046 BC. In East Semitic cultures, the main medicinal authority was a kind of exorcist healer known as an asipu. The profession was generally passed down from father to son and was held in extremely high regard. Of less frequent recourse was another kind of healer known as an ASU, who corresponds more closely to a modern physician and treated physical symptoms using primarily folk remedies composed of various herbs, animal products, and minerals, as well as potions, enemas, and ointments or poultices. These physicians, who could be either male or female, also dressed wounds, set limbs, and performed simple surgeries. The ancient Mesopotamians also practiced prophylaxis and took measures to prevent the spread of disease. The ancient Mesopotamians had extensive knowledge about the chemical properties of clay, sand, metal ore, bitumen, stone, and other natural materials, and applied this knowledge to practical use in manufacturing pottery, faience, glass, soap, metals, lime plaster, and waterproofing. Metallurgy required scientific knowledge about the properties of metals. Nonetheless, the Mesopotamians seem to have had little interest in gathering information about the natural world for the mere sake of gathering information and were far more interested in studying the manner in which the gods had ordered the universe. Biology of non-human organisms was generally only written about in the context of mainstream academic disciplines. Animal physiology was studied extensively for the purpose of divination. The anatomy of the liver, which was seen as an important organ in haruspice, was studied in particularly intensive detail. Animal behavior was also studied for divinatory purposes. Most information about the training and domestication of animals was probably transmitted orally without being written down, but one text dealing with the training of horses has survived. The Mesopotamian cuneiform tablet Lipton 322, dating to the 18th century BC, records a number of Pythagorean triplets 3, 4, 5, 5, 12, 13, hinting that the ancient Mesopotamian might have been aware of the Pythagorean theorem over a millennium before Pythagoras. In Babylonian astronomy, records of the motions of the stars, planets, and the moon are left on thousands of clay tablets created by scribes. Even today, astronomical periods identified by Mesopotamian proto-scientists are still widely used in Western calendars such as the solar year and the lunar month. Using these data, they developed arithmetical methods to compute the changing length of daylight in the course of the year and to predict the appearances and disappearances of the moon and planets and eclipses of the sun and moon. Only a few astronomers' names are known, such as that of Kidinu, a Chaldean astronomer and mathematician. Kidinu's value for the solar year is in use for today's calendars. Babylonian astronomy was the first and highly successful attempt at giving a refined mathematical description of astronomical phenomena. According to the historian A. Abo, all subsequent varieties of scientific astronomy, in the Hellenistic world, in India, in Islam, and in the West, if not indeed all subsequent endeavor in the exact sciences, depend upon Babylonian astronomy in decisive and fundamental ways. Egypt main articles, Egyptian astronomy, Egyptian mathematics, and Egyptian medicine. Ancient Egypt made significant advances in astronomy, mathematics and medicine. 25 Their development of geometry was a necessary outgrowth of surveying to preserve the layout and ownership of farmland, which was flooded annually by the Nile River. The 3, 4, 5 right triangle and other rules of geometry were used to build rectilinear structures, and the post and lintel architecture of Egypt. Egypt was also a center of alchemy research for much of the Mediterranean. The Edwin Smith Papyrus is one of the first medical documents still extant, and perhaps the earliest document that attempts to describe and analyze the brain. It might be seen as the very beginnings of modern neuroscience. However, while Egyptian medicine had some effective practices, it was often ineffective and sometimes harmful. Medical historians believe that ancient Egyptian pharmacology, for example, was largely ineffective. Nevertheless, it applied the following components to the treatment of disease: examination, diagnosis, treatment, and prognosis, which display strong parallels to the basic empirical method of science and, according to G.E.R. Lloyd, played a significant role in the development of this methodology. The Ebers Papyrus c. 1550 BC also contains evidence of traditional empiricism. In classical antiquity, the inquiry into the workings of the universe took place both in investigations aimed at such practical goals as establishing a reliable calendar or determining how to cure a variety of illnesses, and in those abstract investigations known as natural philosophy. The ancient people who are considered the first scientists may have thought of themselves as natural philosophers, as practitioners of a skilled profession, for example, physicians, or as followers of a religious tradition, for example, temple healers. The earliest Greek philosophers, known as the pre-Socratics, provided competing answers to the question found in the myths of their neighbors: how did the ordered cosmos in which we live come to be? 30. The pre-Socratic philosopher Thales (640–546 BC), dubbed the father of science, was the first to postulate non-supernatural explanations for natural phenomena. For example, that land floats on water and that earthquakes are caused by the agitation of the water upon which the land floats, rather than the god Poseidon. Thales' student Pythagoras of Samos founded the Pythagorean school, which investigated mathematics for its own sake, and was the first to postulate that the Earth is spherical in shape. Leucippus 5th century BC introduced atomism, the theory that all matter is made of indivisible, imperishable units called atoms. This was greatly expanded on by his pupil Democritus and later Epicurus. Subsequently, Plato and Aristotle produced the first systematic discussions of natural philosophy, which did much to shape later investigations of nature. Their development of deductive reasoning was of particular importance and usefulness to later scientific inquiry. Plato founded the Platonic Academy in 387 BC, whose motto was, "Let none unversed in geometry enter here," and turned out many notable philosophers. Plato's student Aristotle introduced empiricism and the notion that universal truths can be arrived at via observation and induction, thereby laying the foundations of the scientific method. Aristotle also produced many biological writings that were empirical in nature, focusing on biological causation and the diversity of life. He made countless observations of nature, especially the habits and attributes of plants and animals on Lesbos, classified more than 540 animal species, and dissected at least 50. Aristotle's writings profoundly influenced subsequent Islamic and European scholarship, though they were eventually superseded in the scientific revolution. The important legacy of this period included substantial advances in factual knowledge, especially in anatomy, zoology, botany, mineralogy, geography, mathematics and astronomy, an awareness of the importance of certain scientific problems, especially those related to the problem of change and its causes, and a recognition of the methodological importance of applying mathematics to natural phenomena and of undertaking empirical research. In the Hellenistic age, scholars frequently employed the principles developed in earlier Greek thought, the application of mathematics and deliberate empirical research, in their scientific investigations. Thus, clear unbroken lines of influence led from ancient Greek and Hellenistic philosophers, to medieval Muslim philosophers and scientists, to the European Renaissance and Enlightenment, to the secular sciences of the modern day. Neither reason nor inquiry began with the ancient Greeks, but the Socratic method did, along with the idea of forms, great advances in geometry, logic, and the natural sciences. According to Benjamin Farrington, former professor of classics at Swansea University, men were weighing for thousands of years before Archimedes worked out the laws of equilibrium. They must have had practical and intuitional knowledge of the principles involved. What Archimedes did was to sort out the theoretical implications of this practical knowledge and present the resulting body of knowledge as a logically coherent system, and again. With astonishment we find ourselves on the threshold of modern science. Nor should it be supposed that by some trick of translation the extracts have been given an air of modernity. Far from it. The vocabulary of these writings and their style are the source from which our own vocabulary and style have been derived. The astronomer Aristarchus of Samos was the first known person to propose a heliocentric model of the Solar System, while the geographer Eratosthenes accurately calculated the circumference of the Earth. Hipparchus, c. 190 c. 120 BC, produced the first systematic star catalogue. The level of achievement in Hellenistic astronomy and engineering is impressively shown by the Antikythera mechanism 150–100 BC, an analog computer for calculating the position of planets. Technological artifacts of similar complexity did not reappear until the 14th century, when mechanical astronomical clocks appeared in Europe. In medicine, Hippocrates c. 460 BC, c. 370 BC, and his followers were the first to describe many diseases and medical conditions and developed the Hippocratic Oath for physicians, still relevant and in use today. Herophilos 335–280 BC was the first to base his conclusions on dissection of the human body and to describe the nervous system. Galen 129 c. 200 AD performed many audacious operations, including brain and eye surgeries, that were not tried again for almost 2 millennia. One of the oldest surviving fragments of Euclid's Elements, found at Oxyrhynchus and dated to c. 100 AD. In Hellenistic Egypt, the mathematician Euclid laid down the foundations of mathematical rigor and introduced the concepts of definition, axiom, theorem and proof still in use today in his Elements, considered the most influential textbook ever written. Archimedes, considered one of the greatest mathematicians of all time, is credited with using the method of exhaustion to calculate the area under the arc of a parabola with the summation of an infinite series, and gave a remarkably accurate approximation of pi. He is also known in physics for laying the foundations of hydrostatics, statics, and the explanation of the principle of the lever. Theophrastus wrote some of the earliest descriptions of plants and animals, establishing the first taxonomy and looking at minerals in terms of their properties such as hardness. Pliny the Elder produced what is one of the largest encyclopedias of the natural world in 77 AD, and must be regarded as the rightful successor to Theophrastus. For example, he accurately describes the octahedral shape of the diamond, and proceeds to mention that diamond dust is used by engravers to cut and polish other gems owing to its great hardness. His recognition of the importance of crystal shape is a precursor to modern crystallography, while mention of numerous other minerals presages mineralogy. He also recognizes that other minerals have characteristic crystal shapes, but in one example, confuses the crystal habit with the work of lapidaries. He was also the first to recognize that amber was a fossilized resin from pine trees because he had seen samples with trapped insects within them. Mathematics. The earliest traces of mathematical knowledge in the Indian subcontinent appear with the Indus Valley Civilization, c. 4th millennium BC / c. 3rd millennium BC. The people of this civilization made bricks whose dimensions were in the proportion 4:2:1, considered favorable for the stability of a brick structure. They also tried to standardize measurement of length to a high degree of accuracy. They designed a ruler, the Mohenjo-Daro ruler, whose unit of length, approximately 1.32 inches or 3.4 centimeters, was divided into 10 equal parts. Bricks manufactured in ancient Mohenjo-Daro often had dimensions that were integral multiples of this unit of length. Indian astronomer and mathematician Aryabhata (476–550) in his Aryabhatiya 499 introduced a number of trigonometric functions including sine, versine, cosine and inverse sine, trigonometric tables, and techniques and algorithms of algebra. In 628 AD, Brahmagupta suggested that gravity was a force of attraction. 47-48. He also lucidly explained the use of 0 as both a placeholder and a decimal digit, along with the Hindu-Arabic numeral system now used universally throughout the world. Arabic translations of the two astronomers' texts were soon available in the Islamic world, introducing what would become Arabic numerals to the Islamic world by the 9th century. During the 14th–16th centuries, the Kerala School of Astronomy and Mathematics made significant advances in astronomy and especially mathematics, including fields such as trigonometry and analysis. In particular, Madhava of Sangamagrama is considered the founder of mathematical analysis. Astronomy. The first textual mention of astronomical concepts comes from the Vedas, religious literature of India. 52. According to Sarma 2008, one finds in the Rigveda intelligent speculations about the genesis of the universe from non-existence, the configuration of the universe, the spherical self-supporting Earth, and the year of 360 days divided into 12 equal parts of 30 days each with a periodical intercalary month. The first 12 chapters of the Siddhanta Shiromani, written by Bhaskara in the 12th century, cover topics such as, mean longitudes of the planets, true longitudes of the planets, the three problems of diurnal rotation, syzygies, lunar eclipses, solar eclipses, latitudes of the planets, risings and settings, the moon's crescent, conjunctions of the planets with each other, conjunctions of the planets with the fixed stars, and the padas of the sun and moon. The 13 chapters of the second part cover the nature of the sphere, as well as significant astronomical and trigonometric calculations based on it. Nilakantha Somayaji's astronomical treatise The Tantra Sangraha, similar in nature to the Tychonic system proposed by Tycho Brahe, had been the most accurate astronomical model until the time of Johannes Kepler in the 17th century. Linguistics. Some of the earliest linguistic activities can be found in Iron Age India, 1st millennium BC, with the analysis of Sanskrit for the purpose of the correct recitation and interpretation of Vedic texts. The most notable grammarian of Sanskrit was Panini, c. 520–460 BC, whose grammar formulates close to 4,000 rules which together form a compact generative grammar of Sanskrit. Inherent in his analytic approach are the concepts of the phoneme, the morpheme and the root. Medicine. Findings from Neolithic graveyards in what is now Pakistan show evidence of proto-dentistry among an early farming culture. 54. Ayurveda is a system of traditional medicine that originated in ancient India before 2500 BC, 55, and is now practiced as a form of alternative medicine in other parts of the world. Its most famous text is the Susrutasamhita of Susruta, which is notable for describing procedures on various forms of surgery, including rhinoplasty, the repair of torn ear lobes, perineal lithotomy, cataract surgery, and several other excisions and other surgical procedures. Metallurgy. The woods, crucible and stainless steels were invented in India, and were widely exported in classic Mediterranean world. It was known from Pliny the Elder as Ferrum Indicum. Indian Wootz steel was held in high regard in Roman Empire, was often considered to be the best. After in Middle Age it was imported in Syria to produce with special techniques the Damascus steel by the year 1000. The Hindus excel in the manufacture of iron, and in the preparations of those ingredients along with which it is fused to obtain that kind of soft iron which is usually styled Indian steel Hindia. They also have workshops wherein are forged the most famous sabers in the world. Henry Yule quoted the 12th century Arab Edrizi. Mathematics. From the earliest the Chinese used a positional decimal system on counting boards in order to calculate. To express 10, a single rod is placed in the second box from the right. The spoken language uses a similar system to English, e.g. 4207. No symbol was used for zero. By the 1st century BC, negative numbers and decimal fractions were in use, and the 9 chapters on the mathematical art included methods for extracting higher-order roots by Horner's method and solving linear equations and by Pythagoras' theorem. Cubic equations were solved in the Tang dynasty, and solutions of equations of order higher than 3 appeared in print in 1245 AD by Qin Chu Shao. Pascal's triangle for binomial coefficients was described around 1100 by Jia Xian. Although the first attempts at an axiomatization of geometry appear in the Mohist canon in 330 BC, Liu Wei developed algebraic methods in geometry in the 3rd century AD and also calculated pi to 5 significant figures. In 480, Zhu Chongzhi improved this by discovering the ratio ∫TFRAC 355 113 TFRAC 355 113, which remained the most accurate value for 1,200 years. Astronomy. Astronomical observations from China constitute the longest continuous sequence from any civilization and include records of sunspots, 112 records from 364 BC, supernovas 1054, lunar and solar eclipses. By the 12th century, they could reasonably accurately make predictions of eclipses, but the knowledge of this was lost during the Ming dynasty, so that the Jesuit Matteo Ricci gained much favor in 1601 by his predictions. By 635, Chinese astronomers had observed that the tails of comets always point away from the Sun. From antiquity, the Chinese used an equatorial system for describing the skies, and a star map from 940 was drawn using a cylindrical Mercator projection. The use of an armillary sphere is recorded from the 4th century BC and a sphere permanently mounted in equatorial axis from 52 BC. In 125 AD, Zhang Heng used water power to rotate the sphere in real time. This included rings for the meridian and ecliptic. By 1270 they had incorporated the principles of the Arab seismology. To better prepare for calamities, Zhang Heng invented a seismometer in 132 CE which provided instant alert to authorities in the capital Luoyang that an earthquake had occurred in a location indicated by a specific cardinal or ordinal direction. Although no tremors could be felt in the capital when Zhang told the court that an earthquake had just occurred in the northwest, a message came soon afterwards that an earthquake had indeed struck 400 kilometers (248 miles) to 500 kilometers (310 miles) northwest of Luoyang in what is now modern Gansu. Zhang called his device the instrument for measuring the seasonal winds and the movements of the earth, Hufeng Didong Yi Hufeng Didong Yi, so named because he and others thought that earthquakes were most likely caused by the enormous compression of trapped air. See Zhang's seismometer for further details. There are many notable contributors to the field of Chinese science throughout the ages. One of the best examples would be the medieval Song Chinese Shen Kuo (1031–1095), a polymath scientist and statesman who was the first to describe the magnetic needle compass used for navigation, discovered the concept of true north, improved the design of the astronomical gnomon, armillary sphere, sight tube, and clepsydra, and described the use of drydocks to repair boats. After observing the natural process of the inundation of silt and the find of marine fossils in the Taihang Mountains, hundreds of miles from the Pacific Ocean, Shen Kuo devised a theory of land formation, or geomorphology. He also adopted a theory of gradual climate change in regions over time, after observing petrified bamboo found underground at Yan'an, Shaanxi Province. If not for Shen Kuo's writing, 63, the architectural works of Yu Hao would be little known, along with the inventor of movable type printing, Bai Sheng 990-1051. Shen's contemporary Su Song (1020–1101) was also a brilliant polymath, an astronomer who created a celestial atlas of star maps, wrote a pharmaceutical treatise with related subjects of botany, zoology, mineralogy, and metallurgy, and had erected a large astronomical clocktower in Kaifeng City in 1088. To operate the crowning armillary sphere, his clocktower featured an escapement mechanism and the world's oldest known use of an endless power transmitting chain drive. The Jesuit China missions of the 16th and 17th centuries learned to appreciate the scientific achievements of this ancient culture and made them known in Europe. Through their correspondence, European scientists first learned about the Chinese science and culture. Western academic thought on the history of Chinese technology and science was galvanized by the work of Joseph Needham and the Needham Research Institute. Among the technological accomplishments of China were, according to the British scholar Needham, early seismological detectors Zhongheng in the 2nd century, the water-powered celestial globe Zhongheng, matches, the independent invention of the decimal system, dry docks, sliding calipers, the double-action piston pump, cast iron, the blast furnace, the iron plow, the multi-tube seed drill, the wheelbarrow, the suspension bridge, the winnowing machine, the rotary fan, the parachute, natural gas as fuel, the raised relief map, the propeller, the crossbow, and a solid fuel rocket, the multistage rocket, the horse collar, along with contributions in logic, astronomy, medicine, and other fields. However, cultural factors prevented these Chinese achievements from developing into what we might call modern science. According to Needham, it may have been the religious and philosophical framework of Chinese intellectuals which made them unable to accept the ideas of laws of nature. It was not that there was no order in nature for the Chinese, but rather that it was not an order ordained by a rational personal being, and hence there was no conviction that rational personal beings would be able to spell out in their lesser earthly languages the divine code of laws which he had decreed aforetime. The Taoists, indeed, would have scorned such an idea as being too naive for the subtlety and complexity of the universe as they intuited it. Thanks for watching till end.